Ionic bonding. Remember, ionic bonding is transferring. You have full charge. This is important. Full charge versus partial charge is going to be discussed today. Full charge, full electron transfer means +1 plus -1. So you have full charge difference here that causes electrostatic attraction. It's called a Coulombic attraction. It's a very strong force. Okay? So metal, non-metal, could be polyatomic involved as well. Forms the electrostatic attraction. These are always called salts too, not just sodium chloride, but anything that's an ionic compound is considered to be in the class of compounds called salts. High boiling and melting points, you saw that in the little mini lab activity. And they conduct electricity when they're dissolved in water. And they're usually hard and brittle. So some characteristics there. This was in the other PowerPoint, but you can take a look here. I'm posting this one on Blackboard for you as well. Metallic bonding, the sea of electrons, the positively charged centers, and then the delocalized electrons. That allows for the metals to have certain properties as well. Malleable, ductile, lustrous, conducts electricity, very high melting points, so that means their boiling points are even higher. Okay, and the electrons can flow. Covalent bonds, though, are talking about sharing electrons. These are going to involve nonmetals and occasionally a nonmetal metalloid combination. These are called molecules. They have lower melting points and boiling points. Usually not conduct electricity when dissolved in water. Or not dissolved in water, they just don't conduct electricity because they don't have charges or ions like that. Full charges, I guess I should say. Covalent bonding, similar elements both need electrons, so they share. Two hydrogen atoms here just showing you. They form a single bond sharing two electrons. You know this. And that would be one of the diatomic molecules. And they're neutral. Here showing you another one where we have a diatomic. They form a single bond. That could be F2, I2, Br2, any of those. Okay. Once again, another good way to study all the different characteristics of the three types of bonding here in this chart. You can go through that. It'll be posted on Blackboard. It's also in the other set of notes too, but it's very good for your test coming up. But now, how are the electrons shared? They're shared equally sometimes and unequally sometimes. So this is where we get into polarity. So when they're shared equally, the weakest type of covalent bond are going to be called non-polar covalent bonds. And I believe this is where your notes start. Okay, non-polar covalent, where they share pretty equally. Which picture shows equal sharing, the left or the right? The left, obviously. This one shows equal sharing. The electron cloud is pretty oval around both nuclei. Over to the right, they're not sharing them equally, the electron cloud, or the majority of the electron cloud is spending time along the atom to the right here. Okay? Polar covalent bonds, they share them unequally, and this is going to be where it gets stronger. So the nonpolar covalent bond, you can see the electron clouds don't necessarily have the electrons don't spend the same amount of time around each atom. And one side has more electrons than the other. And then we use these partial charges in here. It's a little delta symbol, delta negative, delta positive, to show the partial charges. So when you have the delta sign there, it's showing a partial charge as opposed to like just plus. Plus is indicating a full charge like ionic here. When you just have the plus or the minus, that's a full charge. Compared to the delta plus, the delta minus, these ones are considered partial charges. Partial charges are weaker than, obviously, full charges, because ionic bonds, ion-ion bonds are going to be way stronger in terms of melting and boiling. You saw that. Now, when we say dipoles, because we're going to be referring to the ones that have the unequal sharing as dipoles, they have two ends to them. One end is going to be partially positive and one end is going to be partially negative. Just like here, if you're talking about the Earth, there's two sides to it, the North Pole and South Pole. It has two distinct ends. So the molecules are going to have two distinct ends, and that's why we call them dipoles. So here, looking at this particular example, the bulge indicated by the electron cloud closer to the atom to the right there. What's that going to tell you? That the left side with not as much of a bulge is the partial positive, and there are less electrons spending time around that particular atom. Over there, the partial negative side, they have more electrons spending more time around there. And this is usually based off of those electronegativity values. The more electronegative element is going to be pulling the electrons closer to them. So in this case, the atom on the right here is more electronegative than the atom on the left. Question? Electrons spending less time around there. Now, the electronegativity values, which is what you're about to use, are going to tell you, okay, the type of bond that you have. We use the electronegativity difference to tell the type of bond between two atoms in a molecule. So, the ability of an electron in a molecule to attract shared electrons to itself is electronegativity. Remember that it increases as you go up the group and to the right. Fluorine is the most electronegative element on the table with 4.0. Now, I will tell you right now, when asked to calculate electronegativity differences, we will give you the chart. You're not expected to memorize this thing. We will give you the electronegativity values. You just need to know how to calculate them. And identify the correct type of bond from your difference. So, most are a blend, okay? And they follow this kind of gradient here. So down here, the electronegativity differences between 0.3 to 0 are going to fall in the nonpolar covalent range where they're pretty much sharing equally. Like 0.4 to 1.6 here is your polar covalent range. Now down here by 0.4 is less polar than something that's like 1.6, which would be a highly polarizable molecule with a stronger bond than, say, the 0.4 one, okay? And then, of course, 1.7 or above, you get into ionic territory where they're full charges, and now they have really super strength, okay? But it is a gradient, so something with a difference of 1.7 for ionic isn't as strong as something that's going to have a difference of 3.3. 3.3 would be the maximum here. So nonpolar covalent bonds, they are shared equally. Their difference is between 0 and 0.3. Some charts will say 0 to 0.4, but just go based off whatever range the charts give you. Polar covalent, the electronegativity differences are going to be between 0.4, 0.5, and 1.6. So you get to 1.7 and above, it's going to fall under the ionic range. Okay? Full electron transfer, you have full charges in ionic. Polar covalent, you have the partial charges, and then of course nonpolar covalent, it's equally distributed, so it's not really got any dipoles in there. Okay? So now what I'd like you to do is go ahead and look over the paper and look at the electronegativity differences. So very simply put, your first example there, they have what? Arsenic and sulfur, right? Arsenic, sulfur. What is the electronegativity value of arsenic? 2.0. What's the electronegativity value for sulfur?
2.5.
2.5. And it really is this simple. So under the change in electronegativity, that part, all you have to do is take the larger number, subtract the smaller number, and show it too. Make sure you do that. So then you get 0.5. And what range do we fall in? So all you have to do is write polar covalent. So I'm going to give you 5 minutes to work on practicing this, and then we will come back to talking about determining polarity of molecules. All right, so now we're going to be talking about polarity. We'll get into intermolecular forces next time, but they are both involved in this PowerPoint, so I'll be posting it on Blackboard for you. Dipole moments, direction of the polar bond in a molecule. The arrow points towards the more electronegative atom. the higher the electronegativity number. Like so, if we're talking about HCl here, the H is of course less electronegative, partial positive. The Cl is going to be partially negative. We use an arrow pointing towards the Cl to show us where the electrons are spending most of their time. So this one has a polar bond in it. Now molecules can have polar bond but not be polar themselves. So this is kind of the issue of figuring out polarity. And polarity of the entire molecule depends on its shape. So they may have polar bonds in them, but they might not be a polar molecule based off the way the atoms are arranged and the dipole moments are. So looking here, polarity depends on the dipole moments and the molecular shape. So let's take a look here. Nonpolar molecules, dipole moments are symmetrical and cancel out. So if you're looking at BF3 here, the fluorines are all going to equally pull on those electrons from the central atom. So there is going to be no side of the molecule that is actually partially negative. So they cancel each other out. And as you can see, we use symmetry. Is the molecule symmetrical? Yes. You have the three atoms all geometrically arranged on the Vesper theory, being spread out by 120 degrees. So anyway you flip the molecule, it's going to be symmetrical, and they cancel out. So looking for symmetry is one of the things. Central atom doesn't have any lone pairs. The ligands are all the same. They're all Fs. So yes, it's going to be very symmetrical. Even though there's polar bonds in the molecule itself is considered non-polar. Looking at another example, for polar molecules, dipole moments are asymmetrical and they don't cancel out. In this case for water, the dipole moments both are directed towards the O. Okay? And if you remember also in the bed-shaped molecule, that water, they had these two lone pairs up here, right, that are pulling some of those electrons to spend more time around the oxygen. And the symmetry is definitely off. This way, the symmetry looks pretty good. But if you try to draw the line this way, you have lone pairs on one side and atoms on the other. So it is definitely an asymmetrical molecule. And you'll notice that of anything that has a lone pair on the central atom, they are going to be asymmetrical in shape and therefore declared to be polar. Okay? So really it's about the symmetry. We will ask you, though, to calculate and determine whether a specific bond is polar or non-polar or ionic, but you will also have to look at the shape to determine if the entire molecule is polar or non-polar. So determining, let's see here, therefore polar molecules have asymmetrical shape, lone pairs, or asymmetrical atoms. So in this case, this is a tetrahedral one, where you have no lone pairs on the central atom, but the ligands are not all the same. You have one H and three Cls. Therefore, the symmetry is going to get thrown off. The dipole moments all go towards the chlorines, and obviously is going to make the electrons spend more time around that chlorine side of the molecule. Then you will have two poles. You'll have a positive H, and the H plus over here, this side is going to be like partially positive. This one down here is going to be partially negative. So you end up with your dipole and a polar molecule. All right, so now we're going to stop because we're not going into IMFs today, but we will continue on. I want you to flip over to the back and we'll go through a few examples together. So in here, your notes over here are showing you also the dipole moments and the unequal sharing, and showing you how to determine the partial positive and partial negative. You're always welcome to pull up the PowerPoint, though, if you'd like to look at other examples. This is a nice little flow chart to follow. Are there one or more lone pairs on the central atom? If you see a yes, then it's automatically polar. Okay? The next question. If there are no lone pairs, well, you have two options. Are all the bonded atoms the same element? Yes. Then it's non-polar. No. You have different ligands, then you're asymmetrical, and you're going to be polar. So, looking at these examples here, the best thing to do for this side of the worksheet is to draw, we're going to draw the Lewis dot structure, identify the shape, and then based off of that flow chart, determine if it's polar or non-polar. So, we've already drawn this one in our notes, so I'll draw it very quickly. This is the one, remember, that has resonance, because you could put the double bond on any of the oxygens. Oops, only need 2 pairs on that one. All right, so which one of you can tell me the shape of this particular molecule? It is T-planar, the trigonal planar, because you have no lone pairs on that central atom and 3 ligands attached, or 3 atoms to the central atom. Now looking here, following our flow chart, does the central atom have lone pairs? No, so now we go to the bottoms. Are all of the ligands the same? Yes, so what does that fall under?
Non-polar.
Non-polar. So this one we would say is non-polar. I know, it's a sort of it's a step-by-step system, and then just wait till we add the intermolecular forces. So based off of that, we can determine that this one has only London dispersion forces because it's non-polar. So we're going to add another layer to this next time. So you got to get really good with drawing it, identifying the shape, determining the polarity. Yes? Yes. Now, any particular one you'd like me to do? Pick one, anyone, yes. NH4 plus, ammonium, good. Let's draw this one. So the N brings in how many electrons? 5, good, and each H brings in 1 times 4, so that's a total of 9, right? However, it has a +1, so what does that mean? We have to take away an electron from it, so now we only get how much to work with? -1, so we have 8. Which one's going to go in the center? N, okay? And then we attach our ligands. There's 4 of the H's, and since this one has is polyatomic with the charge, what do I need to put around it? Brackets and the plus outside. Now, looking at it, I have central atom with 4 things attached, no lone pairs. What shape are we? Tetrahedral. Very good. This is a tetrahedral shape. Tetrahedral. Now, looking at it, no lone pairs on the central atom. Look at the ligands. Are they the same? So are we polar or non-polar? Non-polar. So this one gets an NP. Non-polar. Let me do this one for you. We didn't really touch on the beryllium example because it's not really necessary till AP, but I will go ahead and draw beryllium for you. Difluoride. Yes, this is a metal, I understand, but like boron not wanting 8, boron wanting 6, the beryllium needs 4. Once again, this is an example for AP level, but just so you could see it, this is how you would draw it. Beryllium only needs 4 valence electrons. It's similar to boron not following the rules. You would put Be in the middle. Be brings in 2, the F's, they bring in 7 times 2, so this ends up being 16 to work with. You attach your F's. I just used 4. This goes down to 12. Of course, then the F's get the other 12. So this one ends up being what shape? No lone pairs, 2 things attached. That's going to be linear, good. And looking at the central atom, it has no lone pairs. Are the ligands the same? Yeah, so this one is also non-polar. Once again, I won't give you the beryllium one on the test. That's more of a just an AP thing of knowing that beryllium can behave differently like boron and only needs 4 valence electrons. CHCl3, sure. Let's take a look at that one. Carbon brings in 4, hydrogen brings in 1, the chlorines bring in 3 times 7, that's 21. So that's a total of plus the 4 plus the 1 gives us 26. Who goes in the center? Carbon. Attach your ligands. First ligand is hydrogen, then comes the chlorines. Okay, I used 8, so now I'm down to 18, and guess what? I have 3 chlorines that need how many? 6 each, and luckily I have 18 total. So I'm going to put them around those. Remember, hydrogen's happy with its 1 single bond, it only needs 2 electrons. So here we go, we're going to put the dots around here, 2, 4, 8, 10, 12, 14, 16, 18. Got all the electrons in. Now, central atom, any lone pairs? No. Are the ligands all the same? No, the ligands are not all the same. So this one's going to be what? Polar. And what shape is this? Central atom, 4 things attached. Which one is this? 4 things attached? Tetrahedral. Very good. All right, let's do one last one. How about H2S? 2 times 1 here, that's going to bring in 6, so we have a total of 8 electrons to work with. Sulfur goes in the center. And attach my H's. I've used 4 electrons to do that, so now I'm down to 4. Oh, sulfur needs those 4 anyways. So, central atom, 2 lone pairs, 2 things attached. What is the shape? This is a bent shape one. So, does the central atom have lone pairs? Polar or non-polar? Polar, very good. Any questions? Not too difficult. Like I said, we're adding the next layer. The IMFs come after this. Okay? So keep that in mind.
What makes H2S?
Well, how do I know to draw that bent? Because it's a group 16 or 6A element in the center. So I know it's going to have lone pairs on it.
So only when it's a group.
If it's group 14 or 4A in the center, I know it's going to be linear because it's going to have double and triple bonds because the carbon group ones, remember, have 4 bonds.
Right.
Whereas the oxygen group have 2 bonds, 2 lone pairs on the central atom. Good question.